So welcome to today's lecture. I want to talk today about image histograms. So what is an image histogram? Or we'll start with explaining briefly what a histogram is in general, and then how we can use image histograms in order to analyze the image in order to modify an image. And we start with the first part of this lecture, where we're introducing, again, very basic histograms and how we can, with very simple operations, modify those histograms. And then in the second part of the lecture, we will look into more sophisticated manipulations that we can do with those image histograms. So for the lecture here, we will assume that we are using grayscale images. That means just kind of black-white or grayscale images, no color information is available. But we can basically do the same things we are doing here with an intensity value, so the grayscale value, also with individual RGB channels if that is needed. But for now, let's assume we have an image which is a 2D grid of intensity values. So basically a photon counter counting the number of photons that has reached every pixel, turned into an intensity value. And then we can see this as an I times J matrix, like this matrix over here, or arranged here in a 2D grid, which contains values between 0 and 255. Why 0 to 255? This is because this is 8-bit. This is what we use kind of 256 values to represent different intensity values. Of course, in reality, this is more a continuous function, or at least close to a continuous function given the large number of photons. And if you use the raw channel of your camera, you will probably use 16 bits for representing the individual intensity values, but most of the time in, let's say, standard image formats, they're reduced to 8 bits, and therefore we are considering here values between 0 and 255. But of course, the same would apply if you use a wider range of possible intensity values. So then our image, or grayscale image, can be represented as a matrix, dimensions I by j, in this case very easily, very simply 3 by 3, taking different intensity values. Intensity value of 0 means it's a dark pixel or black pixel. Intensity value of 255 means it's a white or bright pixel. And anything in between is a gray value. For example, here 128 corresponds to this gray value over here. So this is gray, 0 is black, and 255 is white. And so this is how we can encode or describe the image. A bit more formally, this can be expressed as a function. So a function g, where I and j are the pixel locations in our image. And it is a mapping from the natural numbers or neutral numbers, depending on how you represent your image. But let's say the integer values, two-dimensional integer values, onto the possible grayscale values, which is basically a counter between 0 and 255. Again, could be larger in theory if you use a different range of intensity values. So again, for us, this is our values for b from 0 to I minus j and from 0 to j minus 1. Sorry, not I minus j. 0 to I minus 1 and 0 to j minus 1, because we start with index 0 and then go up to I minus 1 or j minus 1. And our grayscale values lie in the range of 0 to 255. Okay, that's how we represent our image as a function. So we interpret our image as a function, and the function takes its input values to integers and maps it to an intensity value. And that's how we use our image, basically as a function. Now let's look at the second thing. What is a histogram? A histogram is basically an approximate representation of the distribution of numerical data. And typically this numerical data is grouped into bins. So let's say values between 0 and 5 or 6 to 10, for example. These could be those what we call so-called bins. And then we basically have a counter how often they occur, or a probability how often they occur. So in general, we have on the x-axis certain elements that we are looking into. And this could be intensity values in our example, but this could be any other quantities for a histogram. And on the y-axis here, we have the number of occurrences or the probabilities. So depending if I normalize it to 1, then we obtain probabilities. Otherwise, we can also use occurrences. So just a counter, basically, how often does a certain element occur? And that's what a histogram typically does. If we now look into image histograms, we're looking at histograms that tell us something about the intensity values that occur in this image. So for an image histogram, we are representing the distribution of intensity values in that image. And again, so the x-axis turns into the possible intensity values. So 0, 1, 2, 3, 4, 5, and so on until we reach 255. And the y-axis again is the occurrences. So for example, how often does a black pixel appear? So if this is a black pixel, intensity value 0, for example, then this is the counts of the probability that a pixel is black. And we can do this for gray pixels and for white pixels, for example. So basically iterating over all pixels of our image and are building this distribution, this histogram representing the possible intensity values of the image and how often they occur. You can also do this a little bit more formally, and those image histograms again are very frequently used tools. Typically represents the function h of g, so a histogram of my image g, for an intensity value g, sorry. And this is basically the number of pixels in my image that take the value g. So if I ask for h0, this would give me the number of pixels that are black. And if I ask h of 255, it says, what is the number of pixels that are purely white? And this is what this histogram function h does. So it counts the number of pixels that take that specific intensity value that is provided here as an argument g. And then we can directly turn this histogram into a probability which basically tells us if we draw a random pixel from our image, what's the probability that this pixel is black? What is the probability that this pixel is white? So this would be, for example, p of 0 or p of 255. And this value can be very easily computed just by taking the quantity out of that histogram over here and dividing it by the number of pixels that we have in our image. So I times j in our example. So the probability of an intensity value is the histogram of that corresponding intensity value divided by the number of pixels that we have over here. Of course, this holds here for a histogram where the size of the bins is 1, representing 1 pixel, 1 intensity value. So from 0 to 255, that means 256 possible bins. If we build an histogram, for example, where we always group 5 intensity values together, then of course we would have a smaller number of intensity values. But in our case, we typically use these 256 different possible bins that we have over here. Okay, so let's make a concrete example. We start with this image that we had before, so a 3 by 3 image. We have a couple of pixels which are black, which contain zeros, those over here. We have 2 white ones and 2 gray ones over here. And this are the actual intensity values stored in this image. So if I now want to build my histogram, I say, okay, how often does the color black occur? So an intensity value of 0. 1, 2, 3, 4, 5. So h of 0 would be 5 for this image. Let's say, how often does the intensity value 1 occur? Oh, never. So h of 1 would be 0. H of 2 would be 0. H of 3 would be 0. Until we reach h of 128. H of 128, again, looking through all the pixels, say, it appears here, it appears here. So h of 128 will be 2, and so on and so forth. And h of 255 will also be 2. So as a result of this, I will obtain this histogram where I just have 3 bins which are occupied with data, bin 0, bin 128, and bin 255. It occurs 5 times the black pixel, 2 times the gray pixel, and 2 times the white pixel. And this then gives me my histogram over the possible intensity values that occurred in my very simplistic image. I can also turn this again into a probability distribution, or the probability of, if I draw a random pixel, what's the probability of this pixel being white or black? Then I would take here 5 divided by 9, because I have 9 pixels overall, and 2 divided by 9. This would then give me the probability values, and if I sum over the whole histogram, which is normalized in that way, then of course I will end up with the number 1, because with probability 1, every pixel it lies in the range between 0 and 255. So this was an example for, or a very simplistic example for this artificial 9-pixel image. I can do the same with a real image. So if I have this image of that cat, for example, And I just built my histogram of possible intensity values, here ranging from 0 to 255, somewhere over here. And then I just draw those lines over here. How often do the individual intensity values occur? And then I will actually obtain this histogram. So we can see there are black pixels over here. There's a lot of dark, so this area is not perfectly pitch black. It's just dark, so it lies in this peaked area over here. And then over the face and the hairs of the cat, I basically have a fairly uniform, not really a uniform, but a fairly uniform distribution of intensity values. But I have no purely white pixels over here. So I'm not going to the full white, which would be sitting somewhere over here in this example. Okay, so the question is now, how do we actually build one of those histograms? So given I provide you with an image, how do I actually obtain this histogram over here? And we can do this by simply iterating over every pixel and then checking what's the color or the intensity value of that pixel, and then increasing the corresponding counter for the individual pixels. So what we basically do, we need to sum over all pixels and check for every pixel what's the intensity value, and then increase a corresponding counter that refers to exactly this intensity value. So how do we do this? We create a vector or an array h with lengths 256. So these are the bins, the number of possible intensity values that I need to store. And then I initialize this vector with all zeros, so it contains zeros, no counts. This is how I start, basically an empty histogram. And then for each pixel ij, I'm iterating over them, I take out the grayscale value of this pixel ij. So this is gij. This was my image function. Use this to refer to the bin in this vector here, which I want to increase, and then add plus plus, which means take the value and increase it by 1. So in the end, what I have, besides this initialization, I have a small for loop which iterates over all pixels and then read out the intensity value of the pixel I'm addressing and increasing the corresponding counter in h by 1. And I do this by just iterating over the whole histogram. That means I need to touch every pixel once in order to compute that histogram. And this is important if I'm thinking about computational complexity. So computational complexity is typically expressed in terms of this O notation, and it basically tells us how many operations do I need in order to compute that histogram or to compute my operation, independence of the input length, so the length of the image, the size of the image. And here n is I times j, so the number of pixels that I have. And in order to compute this histogram, I need to inspect every pixel. So there's no shortcut, because I just need to check every intensity value in every pixel and see what's this intensity value, increase the corresponding counter in h. So the computational complexity is called O of n, so it's linear in the number of pixels that I have. So if I have an image which has twice the number of pixels, then this operation would take twice as long. Or if I have an image which has 4 times the number of pixels, it would take 4 times as long, because there's a linear dependency between the pixels that I have and the computational or the number of operations that I need to do. So again, this is an algorithmic definition of the complexity, which is in the bound. So if it doesn't mean that I necessarily need that many operations, although this is here the case for this example, but it tells me the worst case approximation, so the worst case number of operations that I actually need to do over here. And of course, it also depends on the length of this vector h, but typically the length of this vector h is independent of the size of my image. So even if I have an image which has just 5 pixels or it has 100 million pixels, that doesn't make a difference because the length of the vector h is always identical. So the length of the vector h doesn't really contribute here because I'm only interested in the input size in my image. Okay, so with this very simple algorithm, I can now, given an input image, compute the image histogram that I can then use, for example, for analyzing my image. What I can also do once I have a histogram, I can compute the so-called cumulative histogram. So what's the cumulative histogram? The cumulative histogram is a function which again has the same input range from 0 to 255 and the y value from 0 to n, where n is the number of pixels. And every bin in here, or every value, x value here, tells me how many pixels have that intensity value or a smaller one. So here it was how many pixels have exactly this intensity value. This was the histogram. And here's which have the intensity value or a smaller one. So this is a function which is monotonically increasing because I will only add new pixels with having higher intensity values when I iterate over this function. And so this is basically a cumulative version of that function. Or it's actually the integral of that function, always integrated up to the corresponding x value. So that means the capital H of 0 and H of 0 are identical. Capital H of 1 is H0 plus H1. Capital H5 is H0 plus H1 plus H2 plus H3, 4, and 5. So this is always the sum of the histogram bins which take a smaller intensity value. So I can very easily express this. Capital H of G, so the cumulative histogram, is the sum over all intensity values from 0 to G. So this is the input value over here, summing over the histograms. So this is basically the number of pixels in that image which have an intensity value smaller or equal to G. And this is what we call a cumulative histogram. So basically, it's just the sum of the individual intensity values of my original histogram. Why is this relevant? Because the histogram and the cumulative histogram can be seen as representing the PDF and the CDF, so the cumulative distribution function of the possible intensity values that occur in my image. And again, it can be very easily computed. The CDF, again, taking the original histogram and just dividing it by the number of pixels so that the values go from 0 to 1 here on this x-axis. And so this is basically then the integral over my PDF, again, in a discretized version over here, which tells us how many pixels have an intensity value smaller or larger than a certain value. And so I can compute for example, what is the probability of getting, if I draw a random pixel from my image, what's the probability that this image has a value smaller or equal to 128, for example? Then I would go to 128 here, and then in this case, the probability would be whatever, something around 60% in this example. And that's what I can do with this CDF function over here of my intensity values. And so the important thing to notice once we have defined those image histograms is actually that those image histograms tell us something about the image or what we actually see in the image. So they tell us how the image actually looks like. Not what is depicted there, but tell us something about, for example, the brightness or the contrast of those intensity values. So if I take my original image over here, and this gives me this histogram, the one that I've shown before. And I can take a transformed image, so in this case, this is an image which is darkened. Then I can see that the histogram actually looks different. And what we can see here in the darkened pixels, for example, there seem to be no pixels which are brighter than an average gray. Just because everything which was bright was basically pushed towards the lower intensity values. And you can see this by having a histogram where all the intensity values are squeezed into an area here between whatever, 0 and maybe 120, for example, over here. So we are basically seeing that we can take this histogram, we are squeezing this histogram, pushing this histogram together. We obtain a histogram which looks like this, and this corresponds to the transformed image. So the shape of this histogram, how it looks like, tells me something about what the image actually looks like. So I can see here by looking to this histogram that there are no pixels brighter than an average gray, which actually corresponds to reality if we inspect this image over here. So pushing the image in this direction seems to lead to a transformed image which appears to be darker. It's not only darkness that we see here, we can also see that some of the contrast is lost. And because the contrast is expressed by the variety of those values. And so by squeezing them together, I'm actually also, not only in this case, reducing the brightness, but I'm also reducing the contrast over here. So what happens if we take this histogram and we just shift this histogram to the right? So what we see here is a simple shift to the right. If we do a simple shift to the right, we can see from the original image to the transformed image that this image gets brighter now. But we see actually there's fairly no difference in the contrast itself. And the reason is we just took this histogram and shifted it to the right. You can see here one peak of the maximum number of values, 255, because these are all the values which basically fall out of this histogram. They accumulated over here, which leads to an increased brightness. What I can also do is I can take the histogram and stretch it so that the intensity values really go from 0 to 255 over here, or even larger than 255, what I can see here. So I'm stretching the histogram, and this results into an image which has an increased contrast. So different quantities of the distribution of those intensity values represented by the histogram tell me something about what the image looks like. What about the contrast? What about the brightness of that image? And it turns out that actually the key parameters of this distribution, which are the mean and the variance, are those two quantities which represent the brightness as well as the contrast. So the mean of the intensity values, which I can easily compute over this histogram, tell me something about the brightness, and the variance of the spread of the intensity values tells me something about the contrast in that image. So the mean describes the brightness, the variance describes the contrast, and also if you talk about the mean, we could also talk about the median, which is kind of a robust estimation of the brightness, just by having some areas which are extremely bright with maybe some sky which is up in the image. I can use this as a more robust version of the description of the brightness in here. Okay, so that means if the mean tells me something about the brightness and the variance tells me something about the contrast, that means we can actually generate transformations which change the image, and this way also change the histogram in order to increase the brightness, or in order to reduce the brightness, or to increase the contrast, or to reduce the contrast. So we can use a function, let's call a function f, or a transformation function, where I put in the input, the original image, it gives me a transformed image so that the histogram has certain properties and transforms the image. For example, increasing the variance increases the contrast, we can see over here. So if I have a function which increases the contrast, so which stretches the intensity value, so they really go through the full spectrum from 0 to 255, this will lead to an increased contrast of my image. And there are different functions that I can realize in order to change the image content over here. And typically, we distinguish here three different types of functions, so-called global operators, local operators, and point operators. And for the purpose of this course, we will mainly look here into those point operators. Not the whole course, but for this lecture over here. And the main difference is it's always a kind of transformation function f. It's the question, what is the input and what is the output? So what does this function change? So the global operator takes the whole input image and leads to a new complete output image. So a pixel value somewhere over here can impact the pixel value that is returned somewhere else, somewhere down here. Or the local operator, where the influence is kind of a local region, we may want to take the neighboring pixels into account in order to perform a transformation, change the actual intensity value of an image. We are looking here at point operators where only the individual pixel matters. So we take one single pixel in my input, and this is the only quantity which is a parameter to this function f, which tells me how the output pixel would look like. So only the input, the parameter that I give to this function in form of the single intensity value of that pixel that I'm transforming has an impact to what the output pixel would be. So for example, if I say, take the original intensity value and multiply it by 2, then I can do this with a point operator, because I take this intensity value, I'll multiply it by 2, and we'll get a brighter pixel over here. So this is what I can do with these point operators. If I, however, want to take the neighborhood into account, let's say the output value of a pixel is actually, for example, the mean of all the neighboring pixels in here. That is something that I would need to do with a local operator, something I can't do with a point operator, because then the neighboring pixels would matter. So a point operator maps an intensity value to a new value, to a new intensity value, only taking into account the input intensity value. So if I have an intensity value v, f of v will turn to v new, and there are no further parameters, at least parts of the image, that matter as the input to this function f here. So it's independent from the other pixel intensity values. This is the key thing. This mapping f is independent from neighboring or other pixel values rather than the one that I'm actually using for generating this transformation. And we're looking here into those point operators because those point operators allow us to transform images into new images so that we, for example, can change brightness or can change contrast in our transformed output image. And that's a frequently used tool in image enhancement, image manipulation, so that we generate new images which have certain properties. Okay, let's be a little bit more formal. So what we have with my point operator, I have my operator function f, I have my output image called b, I have my input image a, but again, I'm only putting the pixel, the intensity value in here, not the whole image, only the single intensity value. And I have a further set here of, let's say, parameters to this function f. And those parameters are in my example before, for example, this factor of 2 with which I want to multiply all the intensity values. So there are some parameters for that function f on which can be involved in this operation, but in terms of the input image, it's just this single intensity value. So that I have a function f which has some additional parameters p, but the input is only this pixel value, so this would be aij, and this would turn into bij at the output. So fa, so is the intensity value of a, and a parameter p, could, for example, be expressed with a function that takes a constant value k plus a second constant m, which is multiplied with the intensity value. And this p would be then the parameter vector consisting of k and m. So this is basically a constant offset to this function, and this is a scale factor with which I multiply my intensity image. So that my resulting operator would look like the output image bij is aij, so the intensity value of the input image, multiplied with m plus k. So what basically k does is it basically shifts the histogram. So if I, for example, say k is 10, then all pixel intensity values will be brighter by 10 counts, or 10 possible grayscale values. So this is something which has clearly an impact on the brightness of the image. And then I have, and if k is larger than 0, it means the image gets brighter. If k is smaller than 0, that means the image gets darker. Then I have the factor m, and m has an impact on the contrast because I'm scaling the intensity value. So if m is, for example, a value larger than 1, I'm increasing the spread of intensity values over the whole spectrum. If it takes a value that is smaller than 1, for example, then it actually reduces this and reduces the contrast of my image. So I have this linear function f of a and p is k plus m times a, where p is k, consists of a vector of k and m, and it transforms the image so that we have a transformed mean and a transformed standard deviation, which looks like this. So this is straightforward. So the mean of intensity values in my new image is the mean of the intensity values in my input image multiplied with m and added up with k. And so if this new mean is larger than the old mean, that means I'm increasing the brightness. And if this one is smaller, I have reduced the brightness. And in terms of the contrast, the standard deviation, also the variance, tells me something about the contrast, then it's basically the size or the magnitude of this scalar m, which tells me if I'm increasing or actually reducing the contrast of the image. So if k is larger than 0, we typically increase the brightness. If k is smaller than 0, we decrease it. If m is larger than 1, we increase the contrast. Or if m sits between 0 and 1, we're actually reducing or decreasing our contrast, because this kind of a value between 0 and 1 squeezes the intensity values close together, a value larger than 1, pull them apart from each other, k larger than 0, shift the histogram in the positive direction, k smaller than 0, shift the histogram in the negative direction. And I can also take negative values for m. For example, if I want to create the negative image, so m equals -1, that means an intensity value of 100 becomes -100. Then together with a proper shift of k, in order to have the value still ranging between 255 and 0, I can actually create the negative of an image. And there are a few examples of those transformation functions, also sometimes called tone curves or simple tone curves in photography, which is a function which describes how this mapping looks like. So basically, this is my value of k over here, and the slope of this straight line over here is basically described by m. So this is here m equals 1. This is m being approximately 0.5. Again, m 0.5, m 0.5, and m equals 2 minus 1. So what we can see here in this aerial image over here, this is my original histogram, so my input image, because this is the identity function. Nothing has changed in here. What this function has done, it basically has squeezed the histogram together to 50% of their width, and then pushed it to the top 50% of the spectrum. So this is basically squeezed together and then pushed to the right. I get this. This is an increased in brightness and also a reduction in contrast because the variance is smaller. Here, I'm just have k equal to 0 and m equals to 0.5. So what happens? The histogram gets actually squeezed together and not shifted. It stays here. So the overall image gets first darker because the mean has been reduced, but it also has a reduced contrast because it only uses 50% of the spectrum of possible intensity values. In this example over here, I kept the average brightness compared to the original image because I have here k of 0.2 of the first quarter of the range of intensity values that I have over here. So this is 64. So the mean should stay the same, at least approximately, but I'm squeezing this histogram together here in the middle. So this is a reduced contrast. And here I have completely inverted the histogram, so basically flipped it around, and this gives me the negative image, which is described by a function which looks like this. So these are simple linear functions and that allow me to transform the image and give that original image a different look. By transforming the image, and we can actually see the result of what the image will look like just by inspecting the histograms. So even if you would not see the images itself, this is the input image, these are the possible outputs, you can actually see just by looking to the shape of that histogram on what the transformation actually was. If it's an increase in brightness, a reduction in brightness, change in contrast, or, for example, creating the negative of an image. So these functions here are linear functions transforming our function. But is it actually really a linear mapping from one intensity value to another intensity value? If you look like this, we can see, we can actually illustrate this. So this on the x-axis here, we have the input intensity values A, the output intensity values B, and a linear function that we would have in here could, for example, look like this. And yes, this k plus m times A is a linear function. The only problem that we have is that we actually need to clip those values here. So all the values which are smaller than 0 become 0, and all the values larger than 255 over here will be limited to 255 because that's what my image can represent. And so through this transformation, I'm actually losing some information because all the very bright intensity values and all the dark intensity values will actually be lost, and all the detail in the highlights or in the shadows are actually lost through such an operation because I'm basically clipping those values away which are larger or will be mapped to values larger than 255 or smaller than 0. So we are actually losing some of the information with this function. Of course, we can also have other nonlinear functions that we can actually involve in here to make this even more extreme. We could generate, for example, a pure black and white image. So if we take, saying all intensity values, let's say smaller than 100, should be mapped to 0, and all the other values should be mapped to 255. So generating a pure black-white image, no grayscale, pure black-white, a binary image, so to say. Then we could do this with this very simple function, return, for example, 0 if a is smaller than the threshold t, or another constant value if it is larger. So, for example, if this is 0 and 255, then I would directly generate this black and white image. And if you look to this nonlinear function, this nonlinear function would look like this. So all intensity values smaller than t will turn into black. Everything which is larger than t or equal to t will actually be mapped to the white pixel value and will be a 0 and 1. So this leads to a binary image. We can also do that the other way around and flip it. So everything which is smaller than a certain value is mapped to the high intensity value, the other one to a smaller value. And often when we talk about binary images, we talk about the values 1 and 0 from the binary concept. But of course, you can very easily turn this into a regular intensity value by multiplying this value with 255. But in the end, a single bit is, for these types of images, sufficient to represent one pixel, just saying it's a black or white pixel. That's something we, for example, often use for masking an image or for describing a mask. We can use a binary image, so just values of 0 and 1, for example, saying a pixel is foreground, a pixel is background, or something like that. So that's what's frequently used. We can also do something in between, not doing these extreme steps of just having zeros and ones or zeros and 255s. We can actually make a quantization with a step function which looks like this. So what is this step function doing? It says all the intensity values between 0 and 63 should be mapped to 0. All the values between 64 and 127 should actually be mapped to 1. Everything from 128 to 191 should be mapped to 2, and everything above that should be mapped to 3. So in this case, I have quantized the intensity values and reduced the possible number of intensity values to 4, from 256 possible values to 4 possible values. And of course, this is something that your camera does automatically when it reads out your chip and all the possible intensity values that your chip can actually measure, all the photon counts, and turns them into values between 0 and 255. And then your camera actually does a form of quantization which may look like this. May also look a little bit different, doesn't say that all those levels must be the same, but for the sake of simplicity over here, we can imagine that the camera actually does something like this. This is an extreme quantization, only leading to 4 possible colors, which kind of reduces the possible intensity values that an image can have. If you have our original input image with 256 intensity values, this is just the threshold with 2 just black and white pixels. Here we have 2 different gray values in between, or 6 different gray values in between 0 and 1, so 8 possible intensity values. So I can reduce this, and it's basically a rounding operation of rounding the intensity values from these 256 values into a quantization of 2, 4, or 8. And this is something that I can do with those simple point operators. It's not a linear function anymore. It's a general function, but it's a simple point operator, because the mapping, which color does this pixel, will this pixel result into here, here, or here, doesn't depend on anything else than the pixel value itself. And those point operators can be computed or generated very efficiently and especially used very efficiently, because they are basically lookup tables, or also called LUTs for lookup table. And what it basically is, it is a vector of 256 integer values, and the index gives you the input intensity, and what is stored in that vector is the output intensity. So it's basically a 256 byte long vector. We just need to look at the corresponding position and then get the transformed value out. So something that is very, very efficient to use, and you can update your images very quickly if you store your transformation function f into one of those lookup tables. And I can do this with the simple lookup tables because the output value only depends on one single intensity input value and doesn't depend on any neighboring pixels. If it would depend on neighboring pixels, I couldn't do that in this efficient manner. And those lookup tables, or those so-called tone curves over here, is something that is very frequently used for image manipulation. We can also do this if we have a color image. So far we just looked into grayscale images. If we have an RGB color image, so we have 3 channels, for example, then we don't have a histogram for the individual intensity values for 255 values. We basically have a histogram for all channels individually. So we can have one histogram for red, one histogram for green, and one histogram for blue, just kind of plotted here together onto one value for always RGB intensity value 0, 128, 255, for example. And this is basically turns a single histogram into 3 histograms. And then, of course, I can also do manipulations with the individual intensity color channels. So I can do a color increase in brightness only in the red channel, for example, or reduce contrast only in the blue channel. These are things that I can do by manipulating the individual channels with those functions. And this is something that is very frequently used in photography, and it's basically an adjustment of the tone curve. So if we have here the original input image that we have also seen before, this is basically the histogram that we see here in this gray here in the background, and this black line here is the tone curve. And this is the identity mapping, so that's the input image. And a lot of tools that you can use for manipulating photos, such as whatever Lightroom, Photoshop, or other tools, you can actually play around with this tone curve. So you can actually take that curve and drag values up and down, as I have done that here. So dragging some of the values down, one up, for example, obtaining one of those S-curves over here. You can see this S-curve here has led to a change in the intensity values. And what we have done here basically is increased the contrast of that function by clipping some of the intensity values here in the end close to 0 and 1, and then having here a value which is kind of a slope which is larger than 1, and thus leads to an increase in the contrast of my image. Because so in this area the slope is smaller than 1, so this is kind of a reduction in contrast here in this very dark and very bright values, but here in the main range we have an increased contrast because of the slope which is larger than 1. And again, this function could again be represented by a simple lookup table saying 0 is mapped to 0, 1 is mapped to 0, 2 is mapped to 0, whatever, 3 is mapped to 1, 4 is mapped to 1, and so on, describing this white curve over here. And again, that's called tone curve mapping, which is frequently used in order to enhance images and or provide images with certain properties that we want them to have. So with this, I'm coming to the end of this first lecture. What we have done here today is we have introduced the idea of histograms and using histograms for the intensity values that we have in an image. So the histogram provides us with the distribution of intensity values that I have in my image. I can do this with grayscale images, what we have looked into here, but I can also do this with color images, for example. We looked into certain things like median or variance, mean and variance. So median is just a robustified version of the mean, as quantities describing the brightness and the contrast of an image. And those histograms allow us, by, for example, looking into the mean or into the variance, to analyze the image. And even the histogram itself tells us much more than just the mean and the variance. It allows us to see which areas of the spectrum of possible intensity values have been used, have been overly used, or underused. And it tells us something about the distribution of intensity values in our images. We can then use functions to change those images and change also the resulting histograms. And we looked into very simple so-called point operators today. So we haven't looked into local or global operators. That's something that will happen throughout that course as well. But for now, we focused on the so-called point operators, which only take one input value and map it to one output value. And those operators are very frequently used tools for image processing in photography, whenever it comes to analyzing images, especially if we as humans need to inspect those images, or we use those transformations in order to change the content of the image. And we have looked into very simple kind of linear functions, mainly here some nonlinear functions in order to achieve this. And in the second part of this lecture, we will look into another form of functions that change our image, where we want to design a function so that the output image has certain properties. So far we said, here's a function, let's see what it results in. You can also take another approach saying, I want to have a certain result. How does this function, should this function look like that I actually obtain that result for an input image? And that's something that we're doing in the next lecture, where we look into things like histogram equalization, which is one technique for adjusting intensity values so that we obtain a certain property in our output histogram. So that's all that from my side for today, and hope to see you soon. Thank you.